Good morning, guys. Let us do some problems in permutations and combinations. In this session, we will do slightly advanced problems also, which are useful for CAT. Right. So, in how many ways can seven persons form a ring? Right. So, sitting around a ring or sitting in a circle is different from sitting in a line. Right. So, for example, you and I, we both have to sit around a circle. How many ways are there? We both have to sit around a circle. That means sit around a circle. There is only one way, right? Whatever way, whichever seat I sit, you will always sit opposite me, or whichever seat you sit, there will be two seats, right? Around the circle, around the table, right? There will be two seats. Whichever table I take, whichever seat I take, you will always be opposite to me. There is no left-right concept here. But whereas if two seats are next to each other, like in a straight line, then I can choose the left seat or the right seat. Then there are two options, right? If there are two seats, and if there are two people, if the two seats are in a line, then there is a possibility, right? One person can take the left seat, another can take the right seat, or the first person can take the right seat, and the second person can take the left seat. There are two possibilities, two permutations. But if it is a circle, what is left, what is right? There is no middle seat, there is no left seat, there is no right seat, right? If it is a circle. So, circular arrangement, people sitting around the circle, the number of options would be lesser than in a straight line arrangement. Let us take, for example, let us take three people, A, B, C, right? So, to make the problem more clear, so there are three seats, one, two, three, one, two, three. A can sit here, then B can sit here, or B can sit here, and C can sit here, or the opposite. B will sit here, or C will sit here, which is this. Right? If A is sitting here, B can either sit to his right or to his left, to his right in this diagram or to his left. There is only two possibilities, right? If A is sitting here. Let's say A is sitting here. Then, then also there are only two possibilities. B is sitting here to his right or B is sitting towards his left. Right? There are only two possibilities if A is sitting here also. Let's say there's a third seat. If A is sitting here. Then also there are only two possibilities. B is sitting to his right and B is sitting to his left. But if we closely see, this diagram, this diagram, and this diagram are all same. Even the A is moving here, 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 is here, is here, is here. A is moving, A is sitting in three different seats, but relatively A, B, C position is always same. A is sitting to the right of C, B is sitting to the right of A. Here also, A is sitting to the right of C, B is sitting to the right of A. Similarly, A is sitting to the right of C, B is sitting to the right of A. So the relative position is not changing, right? If you think that A has actually sat at three different places, it is not. This position, and this positions are exactly same. Even though A is changing his positions. In this case, this seat, in this case, this seat, in this case, this seat, but it doesn't matter. So basically, A doesn't have an option, right? So when there are three seats, so how does this work? First, A can sit anywhere. Then the permutation starts. B has a choice. Now whether to sit right to the right of A or sit to the left of B. So first person in a circular arrangement doesn't actually have any choice. Wherever he sits, it doesn't matter. Then the remaining people will have a choice whether to sit to the right, immediate right of the first person, or two persons, second right or third right, fourth right, etc., etc. So, for example, if there are five people have to sit around a circle. First person doesn't have any choice, right? First person will sit anywhere. Then for the second person, first person will doesn't have a choice. That means one choice only. Wherever he sits, it's the same thing. But for the second person, he has four options. There are four seats, right? Four seats. One seat with then for the second person, he can define the seats. He can define the seats like first right of A, right of the first person, or the second right of first person, third right of first person, or the fourth right of first person. Fourth right of first person will become first left of first person. So the seat definition happens. The definition of a seat happens only when one person takes a seat. Only when first person takes a seat. Then only the definition starts. So second seat will have four options. Third seat will have three options because then fourth seat will have two options. Fifth seat will have one option. Right. This is the way how it works. But whereas in a linear arrangement, even first seat also you can define. First seat you can define as leftmost seat or the middle seat or the rightmost seat, whatever. There's a particular definition for each of the seats. But if it is circle, first seat doesn't matter. Whenever someone sits, then the definition starts. Then the relative positioning starts. Whereas if it is a linear arrangement, there is there is by design there is a definition that this is the leftmost seat. Leftmost seat, five people can sit. Then the second seat will be four options like that if it is a linear arrangement. But if it is a circular arrangement, the first seat, there is no left seat, there is no right seat, there is no middle seat, right? The first seat anyone can take. There is nothing called first seat. Once someone takes that seat, then from the second seat onwards, we have definition that this is the seat next to that person, or this is the seat immediately left to that person, etc., etc. So basically, the formula is when there are n people that are sitting around a circle, right? The number of permutations is n minus 1 factorial. That is the formula, right? So for example, if three people have to sit around a circle. If it is a straight line, it is 3 factorial. 3 times, 2 times, 1 time, right? 3 options for first seat, 2 options for second seat, 1 option for third seat, that is 3 factorial. But if it is a circle, it is 2 factorial only, 3 minus 1 factorial, which is what we are getting here also. Essentially, 2 factorial is 2, right? There are actually two arrangements only. This arrangement, this arrangement, this arrangement are all same. This arrangement, this arrangement, this arrangement are all same. So basically, we have two arrangements only. Two ways only people can sit, right? If there are three people. Similarly, if there are five people that have to sit around a circular table, number of arrangements would be 5 minus 1 factorial, which is 4 factorial, right? Now let's take this problem. Seven people have to sit. So first, how many ways they can be arranged? It is 7 minus 1 factorial, 6 factorial, right? Now, seven Englishmen and seven Americans have to sit around a table. No two Americans being together. What does that mean? If no two people have to sit together, then that means every alternate seat is English, every alternate seat is American, right? So now once we sit Americans, then the relative portion again starts, right? Whether I sit with next to the first English person or second English person, the definition of seats will start once you sit all the English people. So all seven Americans will have seven factorial ways, right? Don't get it wrong here. Seven Americans, once seven Englishmen, they can sit in six factorial ways, and once Englishmen are seated, seven Americans they will sit, they have the option again in 7 factorial ways. It is not 6 factorial ways. Because for Americans, the relative position of seats has already started. The definition of seats have already started. Whereas for the Englishmen, because they were sitting at the first, there is no relative position of or relative definition of seats. And the first Englishman seats, he can sit anywhere. Right. Once after that, six Englishmen will sit, leaving one seat, one seat, one seat like this. Right. So it is actually equal to 6 factorial into 7 factorial. English people 6 factorial, American 7 factorial. Right. Not linear. You can think of it the other way also. Even if Americans sit first, it is 6 factorial, and we have to put 7 Englishmen between Americans, and that is 7 factorial, whichever way it is. First 7 people, there are 6 factorial ways. Between this between these 7 people, there will always be seven slots. Now 7 slots will have, we can fill in 7 factorial number of ways, 7 slots and 7 people. Now these 7 slots and 7 people, they are not then this time it is not like a circle. It is not a independent circle, right? If 7 Americans have to sit on a different table, then it is again 6 factorial ways. If 7 Englishmen and 7 American people have to sit on two different tables, then it is 6 factorial into 6 factorial. But here, Americans and British people have to sit on the same table. That too, Americans have to sit between British people. Right. So the definition, once one of these people sit, then the definition starts. Then the slots are not quite independent. Right. Then we can define each of the seat. Each seat is next to this person or next to that person, like that. Hope you understood this. Next one. From 3 cocoa nuts, 4 apples and 2 oranges, how many selections of fruits can be made taking at least one of each kind? We have 3 nuts. Okay, so 3 nuts A, B, C. Let's say cocoa nuts, 3 nuts A, B, C. We can take at least one. So we can take one of them, two of them, three of them. How many ways are there? We can take A, we can take B, we can take C, then AB, BC, AC, A, B, C. Right, 1, 2, 3, 4, 5, 6, 7. 7 types are there, right? In 7 ways we can take, right? From 3 coconuts, there are 7 ways of taking either at least one or more. Either you can take 3 only once, or if you want to take 2, then there are 3 combinations. If you want to take all 3, there is only one combination. Similarly, what is this? 3C1, 3C1 is 3, then 3C2, which is another 3, then 3C3, which is 1. Taking either one of these 3 or 2 of these 3 or 3 of these 3, which is what? 3C1 plus 3C2 plus 3C3. Similarly, 4 apples. You can take 1 or 2 or 3 or 4. 4C1 plus 4C2, 4C3, 4C4. 4 plus 6 plus 4 plus 1. This is 15. Similarly, 2 oranges, 2C1 or 2C2, which is 3, right? All 3 are independent, right? You can take this thing separately. You can take only one coconut and 4 apples, or 2 coconuts and 2 apples, whatever, right? So total is this thing into this thing into this thing, right? 7 into 15 into 3, right? 7 into 15 into 3. There are actually 315 ways of picking, of selecting either, such that there is at least one of each kind, right? Now we have done 3C1 plus 3C2 plus 3C3. Let's look at this formula very closely. 3C1 plus 3C2 plus 3C3 is equal to 7. 4C1, 4C2, 4C3, 4C4 is equal to 15. 2C1, 2C2 is equal to 3. If you look at it little closely, this 7 is 8 minus 1. This 15 is actually 16 minus 1. This 3 is actually 4 minus 1. So what is happening? 3C1 plus 3C2 plus 3C3 is becoming 2 cube minus 1, right? 8 minus 1 is 2 cube minus 1. Similarly, this thing is becoming 2 power 4 minus 1, right? 16 minus 1, right? Similarly, this thing is becoming 2 square minus 1, right? So something is interesting here, right? So what exactly happens? What exactly is the formula is NC1 to NCN, NC1 plus NC2 plus NC3, whatever to NCN is actually equal to 2 power n minus 1. This can be proved with binomial theorem also. For now, you can use this formula ready-made, and you can actually test it with other combinations also. For the case of n equal to 5, 6, whatever. Okay. So basically, what does that mean? If you have to pick 3, if you have some n objects and you have to pick either 1, 2, 3, 4, 5, whatever of those n objects, how many ways are there? 2 power n minus 1, right? In case of coconuts 3, 2 power 3 minus 1 we can directly take, 2 power 4 minus 1 we can directly take, 2 power 2 minus 1 we can directly take. We don't even need to calculate all of this. Okay, but it's good to know to do it this way also, so that our fundamentals are clean. We know how it is happening. Rather than directly remembering the formula of 2 power n minus 1, it is good. It is good to know how exactly it is working also. And please remember this formula, NC1 plus NC2 plus what plus NCN is equal to 2 power n minus 1. This can actually be proved with binomial theorem. Okay, then this is another interesting problem. Right, another interesting problem. This problem also, you don't you don't need to expect this kind of problem in bank exams. This is more of a cat level problem. Okay, find the number of permutations which can be formed out of the letters of the word series. Taken 3 together. We are looking for 3-letter words from this series. So, but the little trick here is the letters are getting repeated. S is getting repeated, E is getting repeated. R, I are same. If all 6 are different, then there is no problem. 6P3 we can directly say. Right? There are 6 letters, all different, and we have to pick 3 out of them. What are the permutations? Then 6P3. But here the problem is 2 are same, and 2 are different. right? We have to pick three letters. Obviously, the number of permutations should be less than 63, right? So now here, here what will happen when there are six letters? There are only two ways of creating three-letter words. Either all three are different or two of them are same. All three same is not a possibility, right? Because there are only two S's or two E's. Three S's, three E's are not there. So there are only two possibilities. One is either all three letters are different or two letters are same, right? Two letters are same. Now, two letters are same. There are only two possibilities, right? Let me erase this. So two same are all three different. There are only these two possibilities. Now, first let's work about the combinations. How many combinations are there? Then we'll talk about permutations also. How many combinations are there? If two same, if you have to pick, how many combinations? Either this or this, right? There are two combinations. When we have two same, total we have three letters, right? When two same means two letters of them are same. So two letters of the same, two same letters. Either we can pick S or can pick E, right? Of these three letters. We are not worried about the order so far. We are just worried about whether there are two S's or two E's. There are two ways, right? And for the third letter, you can again pick one from the remaining three. So we have three options. Basically, for two same letters, we have two options. For the letter which is different, we have three options. Let's say either we can pick either S or E. That is two options. And for the remaining third letter, if I had picked S, then E R A are the three options. If I had picked E, S R A are the three options. So total six combinations are there. Right. In six ways, we can pick three letters so that two are same. When we have letters like this, S S E E R I, we can pick in six different ways so that two of them are same, right? And when we have all three different, we have to pick all three different. Then what are the ways? We have one, two, three, four. We have four different possibilities for C3, right? This is directly for C3. Whether there are two S's, five S's, 10 S's, it doesn't matter, right? So for example, if we are getting confused, let's say you have to pick two letters. You have to pick two letters between 10 ones, 10 ones and 100 zeros. How does it matter whether 100 zeros are there, 100 ones are there, 10 ones are there? There is only one way, right? There's only one way. Picking two letters so that they are different, right? Even if there are 100 ones or 10 ones or 2 ones, it doesn't matter. When both the numbers have to be different, we are not worried about 0 1 1 0 and all. The permutation we are not worried. We are just worried about combination. In how many ways from 100 ones and 100 zeros we can pick two numbers so that both are different. There is only one way, right? Whichever one you pick, whichever zero you pick, it doesn't matter. Both have to be different. You have to pick 1 1 1 0. So number of ones, number of zeros, it doesn't matter, right? If it is about order, then there are two ways: either 0 1 1 0, right? If both digits have to be different and two numbers have to be from, then 0 1 and 1 0. There are only two ways. The number of ones and number of zeros doesn't matter. Similarly, number of S's, number of E's doesn't matter. If you have to pick three different, all S's will become one option only. All E's will become one option only. R is one option, I is one option. So there are only 4C, three different ways. Here in this case, 10 ones, 100 ones, 100 zeros doesn't matter. It will become two numbers, two different numbers from ones and zeros. One all become one set, zero all become one set. This is 2C2, which is equal to 1. Right? The number of digits doesn't matter. Here also 1, 2, SS will become one set, E's become one set, or I. So there are four different sets of digits or letters. Then we have to pick three out of them. So 4C3. Right? 4C3. These two are about combinations. Now once we have three letters. In the first case, we have three letters. Then two of them are side. How many ways they can be ordered? Earlier also we discussed. It is 3 factorial by 2 factorial into 1 factorial. Because two of them are same. How many ways they can be arranged? When three are there. When three are there, all three are different. Then it is 3 factorial. When some of them are same, then obviously the number of ways they can be arranged will be reduced. If all three are same, let's say all three are same, all three are ones only, all three are S's only, what will that happen? Then there is no way. There is only one way, right? So then it becomes 3 factorial by 3 factorial, right? How many ways, how many times something is being repeated, those many times our number of permutations will go down, right? If everything is repeating, then there is only one way. If there are three S's, all three S's are repeating, there are no distinct letters, then 3 factorial by 3 factorial, which will become only 1. Obviously, right? If everything is S, then there is only one way of writing the word, right? So in this case, all three are different. So in this case, it would be 3 factorial. Right? All three are different, it will be 3 factorial. So basically, we can make these many combinations and these many permutations of each combination. So this one, with this, how much we'll get? 6 into 3 factorial by 2 factorial is 3. This is 18. And in this thing, 4C3, 4 into 4 into 6, this is equal to 24. So 24 plus 18 total is 42 is the correct answer. There are 42 ways where you can create 3-letter words out of this 6-letter words when 2 plus 2 are actually 2 letters are repeating, and two letters are also repeating. Right. This is the way we have to calculate. Where when all three are different, how will it work? When two of them are different, two of them are same, how will it work? Right. Next, this is another important problem. Again, cat level problem. There are p points in a plane, none of which are same in a straight line, with the exception of q. There are p points. Let's say there are 10 points. If all 10 are not any, if no three of these 10 are on the same line, then what will happen? You pick any 2 points, then a straight line will be formed, right? So PC2, right? You can pick just 2 points out of P. Then it is PC2. Number of straight lines would be PC2. But here problem is few of them are on the straight line. So in this queue, if you pick any two, they will still all, let's say three of them are on the straight line, right? Three of them are already on the straight line. 1, 2, 3. Even if you pick these two or these two or these two, it doesn't matter. They'll all still give the same straight line. So these many straight lines are getting double counted. Right. If Q of them are there, then QC2 straight lines are getting double counted. Right. QC2 straight lines are still, they all will become the same straight line. Right. So PC2 minus QC2. But we cannot remove all the QCTs because they should add at least one of them. Right. If you remove QCTs, this entire line will go. But this line, even though it is counted 20 times, we should count at least one time. We should count one time only, not at least. So we will remove all this 20 plus only once we will add. Right. PC2 minus QC2 plus 1 is the correct answer. Right. Right. So one line we have to count. Let's say if it is in the case of triangles. Let's triangles. If all P points are are completely different. If no three of them are on the same point, same straight line, then PC3 number of triangles, right? If no three are on the same line, then obviously you can create in the if no 3 points of these P points are on the same line, then actually you can pick any 3 points and can make a triangle out of them. So PC3. But the problem is some Q points are on the same line. So basically, these Q points, QC3, whatever the combinations, QC3 combinations, there is no way of creating a triangle of this QC3 combinations. So you can directly separate PC3 minus QC3. In the case of straight line, you have to add 1 because that 1 will become a straight line. But in this case, this 1 is not a triangle, right? So that's why there is no need to add. QC3 is still a straight line. QC2 is also a straight line. QC3 is also straight line, whereas PC3 we are talking about triangles. So triangles, originally these many triangles were formed if there are no 3 points such that they are on the same line, but these many points are all on the same line. These many points they will not create triangles. There is no need to add one because these are anyway straight lines only. These are not triangles. In this case, these are straight lines. So we cannot completely remove all of them because all of them all QC2 will refer to the same straight line. There is one line. So that one line we have to add back. Okay. Another interesting problem. This again little advanced. Find the number of selections and of arrangements that can be made by 4 letters from the word expression. Right. Earlier we had looked at series. Here it is about expression and 3 and 4 letters. Right. This is also a little tricky. So, for example, E is repeating twice, S is repeating twice, then X, P, R, I, O, N. Total 1, 2, 3, 4, 5, 6, 7, 8. Right. 1, 2, 3, 4, 5, 6, 7, 8. 8 different letters are there. Right. Now, when we have to make 4 letters, 4 letter word. 4 letter word, how many ways it can be possible? Either two of them are same, 2 plus 2, right? Both E's and both S's. That is one option. Or one of the twos, 2 plus 1 plus 1. Two are same, one remaining two are completely different. Here, first two are same and another two are same. Here, one of the two are same and remaining two are different. Or all four are different. There are only 3 ways, right, of creating a 4 letter word. Either we create such that 2 plus 2, 2 letters are of one kind and 2 letters of the another kind, or 2 letters of the one kind, remaining two are different, or all four are different, right? Now 2 plus 2, right? To create 2 letters of one kind and 2 letters of the another kind, how many options are there? How many combinations are possible? Only two. Either, right? How many combinations are possible? So if 2 plus 2 have to be taken. 2 E's and 2 S's. How many ways are there? There is only one way, right? There are no 2 ways because there are only two combinations. You have to take 2 plus 2. There is only one way. E's and S's, right? Next, if you have to take two same and one different, another different. How many ways are there? For the two same, you can pick either this or this, E's or S's. Right, that is 2. And then for the remaining 1 plus 1. Remaining 2 you have to pick from how many? If you have picked E's, then 1, 2, 3, 4, 5, 6, 7. You have 7 options. Similarly, if you pick S also, you have 7 options. Out of the 7 different letters, you have to pick 2. Right, 2 into 7C2. Similarly, you have to pick all 4 different. All 4 different means total 8 different letters are there, 8C4. This is all about combinations. Here 1 combination, here 2 into 7C2 combination, here 8C4 combinations. Now, in this case, we have 4 letters. 4 letters, 2 are same, 2 are same. How many permutations are possible? 4 factorial by 2 factorial into 2 factorial. Right. So total permutations is 1 into this, which is actually equal to 6. Similarly, in this case, 4 letters are there, 2 are same. 4 factorial by 2 factorial. So 2 into 7C2 is 42. 42 into this thing will equal to 504. Similarly, 8C4, here all 4 are different, so 4 factorial. 4 factorial permutations, 4 letters, all 4 are different. So 4 factorial permutations are possible, 4 factorial words are possible. So 1680, 8C4 into 4 factorial. So total is 2190. Right, hope you understood this. Another similar problem, examination. Examination again, 4 letter words. Here, E is once, X is once, A is twice, M is once, I is twice, N is twice, T once, O once. Similarly, let's like the same problem. Either two are same or two are different. Either 2 plus 2, 4 letter words, right? Two same, two same. Right. Or two same, remaining two are different, or all four different. If 2 plus 2, 2 plus 2, so first two are same. We have three combinations. We have three, either we can pick E, A and I, or A and N, or I and N. We have three combinations, right? We have three twins, of which we have to pick 2 plus 2, two twins, right? 3C2, right? There is three different ways, right? So similarly, 2 plus 1 plus 1. For the first two, again, either A, I, N, three ways. And then for the remaining two, how many letters are there total? 1, 2, 3, 4, 5, 6, 7. Sorry, 1, 2, EX, 1, 2, 3, 4, 5, 6, 7, 8. Total 8. 1 you have already picked. So 7C2. 3 into 7C2. Similarly, of all four are different. Total 8 different letters are there. 8 different letters, so 8C4. Similarly, for the first four letters, in this case 4 letters, 4 factorial by 2 factorial into 2 factorial. This is the number of permutations. In the second case, it is about 4 factorial by 2 factorial because 2 are getting repeated. In the third case, divided by nothing because all 4 are different. So this into this plus this into this plus this into this is the final answer. I think you can do that directly. Right. This is another very tricky problem, very important problem. This is again for CAT level, not for SBIPO and all. This is CAT level problem. So here, find the sum of all numbers greater than 10,000 found by using the digits 1, 3, 5, 7, 9. Right. This is a very interesting problem. So how many numbers can be created? So we have 5 digits. All 5 factorial numbers will be greater than 10,000, right? All of them are greater than 0. All numbers that are created out of this 1, 3, 5, 7, 9 will be greater than 0. Basically, for what are all the numbers that are created with these 5 digits, we have to find sum of all those digits. Okay, basically we have 5 factorial numbers, right? So now if you see 1, 3, 5, 7, 9, 1, if 1 is in this digits place, units, tens, hundreds, thousand, 10,000, 10,000 place, how many numbers are there? If 1 is here, if 1 is here, remaining 4 numbers can adjust themselves in 4 factorial ways. If 1 is here, there are 4 factorial number of numbers, 4 factorial number of numbers where 1 is in 10,000's place. Similarly, if 1 is here, there are again 4 factorial number of numbers, right? Because the remaining 3, 5, 7, 9 can adjust themselves in the remaining 4 slots in 4 factorial ways. Similarly, here, wherever 1 is there, when 1 is here, there are 4 factorial worth of numbers, right? So wherever 1 is, if 1 is here, 4 factorial is what? 24. There are 24 numbers where 1 is in the units digit. There are 24 numbers where 1 is in the tens digit. There are 24 numbers where 1 is in this digit, etc., etc. Right. Total how many numbers are there? Total 5 factorial numbers are there. Total there are 120 numbers, right? Total there are 5 factorial. 1, 2, 3, 4, 5, 5 factorial numbers. Of this 20, of this 120 numbers, 24 numbers have 1 in 10,000 digit, 24 in 1,000, 100, 10, like this. Right, they will be distributed like that. Right, of the 120 numbers, 24 numbers are Z, 1 is here, and 1 is here, another 24, another 24, 1 is here, likewise. Similarly, for the other 4 numbers also. 24 numbers will have 3 here, 24 numbers will have 5 here, 24 numbers will have 7 here, 24 numbers will have 9 here. Similarly, 24 will have 3 here, 24 will have 5 here, all the same. Right, total 120 numbers. These are all the permutations that are possible. Now, when 1 is at these different places, what is the total sum? When 1 is here, it will be counted as 1 only. We see here, it should be counted as 10, right? 1 and here 0. So the sum of all these numbers, sum of all the ones is actually 4 factorial into 1 plus 10 plus 100 plus 1000 plus 10,000, right? We are not worried about 3, 5, 7, 9. Whenever ones are there, what is the contribution of ones into the total sum. Total sum is here 1 will contribute as 1 only, here 1 will contribute as 10, here 1 will contribute as 100, here 10,000, here 10,000. So 4 factorial into 1 plus, so this is 4 factorial into 1, this is 4 factorial into 10, 4 factorial into 100, etc. So 4 factorial into 1 plus 10 plus 100 plus 1000 plus 10,000. So 4 factorial into 11111. This is the total contribution of 1. Right. Similarly for 3. For 3, what exactly is it? How exactly will it become? It is 3 plus 30 plus 300 plus 3000 plus 30,000. Right. 4 factorial into 3 plus 30 plus 300 plus 3000 plus 30,000, which is equal to 4 factorial into 3 into again 5 ones. Right. Similarly 5 also. 4 factorial into 5 into 5 into 5 ones. 7 fact. Similarly here also 4 factorial into 7 into 5 ones. Right. So that is the total sum being contributed by each of these each of these 5 digits. So what will be the total sum? Total sum is contribution of 1 plus 3 plus 5 plus 7 plus 9. So which is equal to 4 factorial into 1 plus 3 plus 5 plus 7 plus 9. This becomes how much? This becomes 25. 4 factorial is how much? 24 into 25 into 5 ones, right? Which becomes 5 ones, which will become 600 into this thing, which is 66666 and 2 zeros, right? So 24 into 25 is 600. 600 into 5 ones, which is 5 sixes and 100. So this is the total sum of all the digits. This is an interesting problem. Right? This is an advanced level problem. One more advanced level problem. I'll give it as exercise. Please do it. This is also something similar. I'll give a hint here. Here the hint is, it's the same thing. All numbers greater than 10,000. But the problem is, 0 is also there. Right. Earlier it was 1. If 1 is there, all the numbers that are created, we can directly do. But here, what will happen is, when 0 is there, all numbers that are creating with 0 as the first place. Right. 1, 2, 3, 4, 5. Wherever 0 is the first place, these all, they don't contribute to the sum, because these are all definitely less than 10,000. Now how many numbers have 0 in the first place? This problem is equal to all the sum of numbers which have 2, 4, 6, 8. Sum of all numbers, sum of all 4-digit numbers. Sum of all 4-digit numbers. Okay. Sum of all 4-digit numbers with these numbers 2, 4, 6, 8. This is equal to calculation of sum of all 5-digit numbers of 1, 3, 5, 7, 9. The same calculation works, but here we have to do two calculations where all sum of 5 digits with 0 also, sum of all 5 digits, all 5-digit numbers 0, 2, 4, 6, 8. 468. This is what we have to do. Then we have to subtract minus sum of all 4 digit numbers which are created out of 2, 4, 6, 8. So we have to do the same problem rather twice and subtract this one from the other one. So that is the trick. Please do it yourself. If any doubts, please message and then we'll pick this up again. Thank you guys. All the best. Hope you have understood. These are slightly advanced problems, but these are necessary for CAT and GMAT level preparation. Hope you understood this. Any questions? Anyway, please comment. We'll pick this up again. All the best. Bye bye.